So there's another form of proof that uses a lot of the same techniques, but it's called indirect proof. And we still get there, but the path that we take is very meandering. And it, it's based off of two principles. One is a proof by the contrapositive, and we know that the contrapositive of an implication, so P implies Q, has a contrapositive, which is not Q implies not P. And these are equivalent. So if I can show that not Q implies not P, that's really the same as showing P implies Q. But sometimes we find that it's actually easier to show the contrapositive than it is to show the initial implication. The second form of proof is proof by contradiction. And that is, if we want to show P, sometimes it's really hard to just show that that's true. But if we can show that assuming that P is false leads us to a contradiction, now we've got something. So let's look at proof by contrapositive. So suppose we're trying to show something of the form P implies Q by its contrapositive. That is, we want to show not Q implies not P. To show this, we're going to assume not Q and then show that not P is true as well. This is called indirect proof. We're getting there, but we're taking this meandering path. We're going to show that this is true by looping past the contrapositive and bringing it back to what we wanted to show in the first place. And why does this work? Well, it works for what was shown on the previous slide. That's because implication, it's equivalent to its contrapositive. And so showing one is the same as showing the other. So let's look at an example of proof by contrapositive. And that is we want to prove that if n is an integer and 3n plus 2 is odd, then n is odd. So this is our p and this is our q, and we want to show that being an integer such that 3n plus 2 is odd, then n is odd. We're going to do that by assuming not q. So this is the equivalent of not q. We're going to assume that consequent n is odd is false, that n is even. And then things will follow. So if n is even, then n is equal to 2k for some integer k. 2 times some other integer. But now, if that's the case, then I can stick that in to 3n plus 2. And what happens is that we've got 3 times 2k plus 2. That's 6k plus 2. And I can pull a 2 out from all of that. So from this, I can pull out 2, and I get 2 times 3k plus 1. Well, now I know that 3k plus 1 is an integer. It's some integer j. And that means the whole thing, 3n plus 2, is equal to 2j. But 2j is even. Since we've shown that not q implies not p, then p implies q must hold as well. And what that says, if n is an integer and 3n plus 2 is odd, which is not even, then n is odd, also not even. So finally, we'll take a look at another form of indirect proof, proof by contradiction. And that is, if we want to show that P is true, then we're going to do it by showing that starting with not P leads us to a contradiction. So we'll assume not P, and then we'll derive some contradiction, some situation that just can't occur. For instance, if P must also follow, then we have a situation P and not P. Well, that we know can never be true. And so in showing that not P implies a contradiction, it follows that the contrapositive of this, which we know is equivalent to that implication, is also true. And so the contrapositive of not P implies false is that not false implies not, not P. But this is the same as true implies P. And what do we know? If the antecedent of an implication is true, then P must also be true. And so in this case, that's the same as saying P is true. So let's take a look at what this looks like when we apply it to a form of proof. Here's our example of proof by contradiction. So we want to prove that if you pick any 22 days from the calendar, then at least 4, could be more, at least 4 must fall on the same day of the week. And so that's our proposition, P. So what does not P look like then? Well, not P is assuming that this isn't true. So we want to assume that it's not true that if you pick any 22 days from the calendar, then at least 4 must fall on the same day of the week. So instead, we can assume that no more than 3, so less than 4 days of the 22 days fall on the same day of the week. That's our not P. How do we arrive at a contradiction? Well, this involves something really fun, and that is the pigeonhole principle. Always a favorite of mine. I apologize immediately for my drawing skills, but the pigeonhole principle goes something like this. If I have more pigeons than I have pigeonholes, so homes for them to go live in, then no matter how I handle this, at least one of the pigeonholes is going to have 2 or more pigeons in it. So it could be they all fly to the same hole, but this third pigeon is going to have to double up. So we could have 2, 1, 3, and 0, but no matter what we do, at least one of the pigeonholes is going to have more than one pigeon in it. Well, that's a fun rule, except how does that apply in this situation? Well, in this situation, we have 22 days and we want to place them into days of the week. So I have the days of the week: Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday. And these are my pigeonholes. And I have 22 days that I have to place into those pigeonholes. So I know that I can place 7 of them, no problem. Everybody goes in a different place. And in fact, I want to put 3 or less. Well, as soon as I put 3 in each, so I want no more than 3 fall on the same day. So if I put 3 in each, well, that's 3 times 7 days. 3 times 7 is 21. So there are only 7 days of the week. So while we could have picked 21 days for this to work, there's no other place for us to put that 22nd day. At least one of those days of the week will have 4 days within it. So this provides our contradiction. It contradicts the assumption that we have picked 22 days such that this would work. And that's how we wrap this up. That's our grand finale. That's where we add our rubber stamp, or in this case, a rubber duck, a QED, seal of approval that this proof is complete. And with that being said, happy Thanksgiving.